Hey, good morning. And today we are going to keep working on Chapter 7. We'll continue on Chapter 7. So for Wednesday, you want to read Section 7.5. And you have homework due not this Friday, but a week from Friday. So it's still a ways to go, but we'll start talking about it. Now, last class we talked about putting an electrode in the body and then using it to stimulate nerve axons. This week, today, we're going to talk about putting an electrode in the body and using it to record extracellular potentials produced by nerves and muscle. So we're still going to be dealing with electrodes, but under a little bit different use. So I'm going to look specifically at what extracellular potentials are produced by nerves and muscle. So we'll start with nerve axon, and then we'll begin to turn our attention more to cardiac tissue. So let us take a look at what we're saying. Here you have a nerve axon. And you have an action potential or some sort of electrical activity in the nerve axon. And that's going to produce currents going through the membrane and into the extracellular space. So if we just take a little area of current here, or area of the membrane, and we have some current coming out of that. So we'll call this Jm, the current, at least the current density times the area. This thickness will be dx. And we want to ask ourselves, what electrical potential do we see out here? We're going to call this point, this distance here, r. And then we can add up, if we have current coming out all along the axon, we can just add them all up to get the total response. Okay, so what is essentially the extracellular potential? Well, if we're quite a ways away from the axon, this axon acts essentially like a point source of current. So current's going to be coming out in all directions. It's going to look like a single point source. So does anybody remember what the potential is produced by a point charge in electrostatics? How does that depend on distance from the charge? Anybody remember your introductory physics? Well, forces and electric fields fall off as 1 over r squared, but we're talking about electrical potential, which is more like a electrical potential energy. At least it's electrical potential energy per unit charge. It falls as 1 over r. You take the derivative of the potential and you get the electric field. The derivative of 1 over r is 1 over r squared, and you get Coulomb's law back. So, it's actually the equation we're going to be using is this. The current, this is the total current coming out of this axon, divided by 4 pi sigma E r. Sigma E is extracellular conductivity. Now this looks a lot like what you saw in electrostatics, except instead of charge Q, we have the current I. And instead of epsilon or epsilon naught, the constant for electrostatics, we have the conductivity. It's a little bit different because when you're dealing with a conducting fluid, you have to apply the current, and then the current causes charge to move in the conductor, unlike a point charge just in a vacuum where it's going to produce an electric field but no charge moving. So the equation is analogous to what you see for electrostatics, slightly changed to take into account that we're in a conducting medium. All right, so we have to relate now the current to this current density that we calculate coming out of the membrane. Well, current density is current per unit area. So the current is just going to be the current density times the area. And the area is this area of this little part of the membrane. And that's going to be the thickness of the membrane times the circumference, or 2 pi a. So delta x, I'll call it dx. And 2 pi, and we'll use a for the axon radius. So that would be a. So what we find is that it depends on dx, and we then can integrate over x, and we can calculate the whole current coming out. So that a little more accurate way to express the extracellular potential is going to be, let's put this in for I, but we're going to say that's really the extracellular potential over one small region. We're going to integrate over all x, and let me put a little space here because we're going to integrate, but we have some constants coming out. We have 4 pi sigma e, and the current is Jm 2 pi a dx, and you have a 1 over r, which may change if you go to different regions along the axon. This distance may change a little bit. So this is our basic expression. We're not going to be able to avoid integration at this point. If we want to figure out what the extracellular potential is, we really have to integrate along the axon. Now, let us remind ourselves of a few things. We found that when we were doing the cable model, the current only goes through the membrane if it changes, the current along the axon changes. So you have to, if it's related to, well, some constants, dji dx. Ji is the current coming down here. There's a current Ji going out, and if that's changing with position, then the Kirchhoff's law says there's some current coming out of the axon. That's review. And also review, Ji is minus sigma I dv dx. Di, really? This says that these currents inside are produced by voltage gradients, where the intracellular conductivity is conductivity inside. And therefore, if you put these two together, you get the Jm, there's two minus signs, is a sigma I over 2 d squared vi dx squared. Really, this is just what we had with the cable model. If you remember, this is the second derivative with space, and then that's equal to a capacitive term, first derivative in time, and a conductive term. So it's really, this part is nothing new, but we're going to put it in here for Jm. And what we'll get is, okay, 1 over 4 pi sigma e. Now let's see what we have here. We have a 2 pi a that can come out. When we put this in for Jm, we'll get an a sigma I over 2 will all come out. And what do we have left is d squared vi dx squared times dx. Now, a lot of stuff is going to cancel. Pi's will cancel. You have a 2 will cancel that 2. And you'll have a couple of A's. I have a 4 left. So you'll get sigma I over sigma E, a ratio of the conductivities. You'll get an A squared, A and A, divided by 4, and then you get this integral, v squared ve dx squared, 1 over r. Now, what's this tell us? Well, this is intracellular, second derivative. This says that the extracellular potential is going to look something like the second derivative of the intracellular potential. Not exactly, it's got this integral, but if you're fairly close, 1 over r is going to be very small, so this quantity will be big only when you're very near, only when you're in a short region around the axon. So very close to the axon, essentially the extracellular potential is going to look like the second derivative of the intracellular potential. So let's just remember what those look like. The intracellular is at rest, and then during act potential comes up, and then comes back down, kind of like that. And if you look at what the second derivative of that looks like, well, where it's flat, there's no derivative. Here, it looks kind of fit by a parabola, so it's a kind of positive. Then here, it's fit sort of by an upside down parabola, so it's going to go bigger negative. And then here's sort of an upside down parabola, upright side up parabola again. So you're going to get something that looks like sort of like this. So extracellular potentials have a more complicated shape than intracellular potentials. So that's the first thing we learned. Second thing we learned is I want to look at the amplitude. This is 100 millivolts from rest up to the peak. What is it for extracellular potentials? Well, we can do some sort of hand waving here. VE is approximately, well, you have this ratio sigma I over sigma E. Sigma I, salt water. Sigma E, salt water. They're not too different. So we're going to just approximate this ratio as 1. You have A squared over 4, and now you have D squared, second derivative of VI. Well, that's approximately the intracellular potential, and divided by delta X squared, or you can approximate this as VI over some distance squared. And what distance do you use? Well, sort of a distance characteristic of how the potential changes along the axis, which is order of magnitude at least, like the length constant. So we'll put the length constant squared down here. And then you also have your R, because you have a 1 over R. And then you have your dx, so how far you can integrate? Well, you can integrate sort of over a distance by which the potential changes, which is again roughly lambda. So this is roughly lambda, and your dx squared is roughly 1 over lambda squared. And you work all that out, and what you get is a squared over r lambda, maybe a factor of 1/4. So let's n times vi. So a squared r and lambda. Now a is the axon radius. That's usually much smaller than lambda, because lambda is like a millimeter, length constants. Axon radii for a lot of nerves in the body, or a lot of axons, are maybe 5 microns, 10 microns. So A is a lot smaller than lambda, and usually A is going to be smaller than R, because R is the distance from the electrode. So if your electrode is, say, a millimeter from your nerve, then R is going to be a lot bigger than A. This only violates if you have an electrode very, very close to the nerve. So in other words, this quantity in parentheses is going to be really small. Small number divided by 2 larger numbers. So that means that VE is very small compared to VI. So this might be 100 millivolts, but this is going to be more like 1 millivolt. It's much smaller. Extracellular potentials are very small, and they're difficult to measure. They are larger as you're closer. Oftentimes when you're going to be measuring extracellular potentials, you're going to be measuring them on the surface of the body, so you don't have to poke electrodes in. You can poke electrodes in and measure them deeper, but then that's a little bit invasive. But usually for the electrocardiogram, the electroencephalogram, for most measurements, you put an electrode on the skin surface. And then you're going to be measuring millivolts, maybe even smaller, maybe even 100 microvolt type of a signal. So you don't see these large 100 millivolt signals in the extracellular space. So that's sort of why we've ignored them before when we developed the cable model. Initially, we sort of assumed the extracellular space was grounded. Pretty good assumption. To assume the extracellular space is grounded if you're just dealing with action potentials. Okay. Questions on that so far? We're going to explore this a little more. What I want to do now is a problem from the book. So I'll keep that picture there. Erase this. Now, this is going to be a sort of a gross simplification. This is problem 7.2. Okay, it's not one of your homework problems. However, problem 7.1, which is one of your homework problems, is very similar to this. So, and it's actually similar to, I believe, one of the problems you looked at in one of the previous homework. So problem 7.2 says, an axon is stretched along the x-axis. At one instance in time, its impulse traveling along the axon has the form shown by a graph. And it shows the graph. The electric conductivity inside is sigma I, radius A, outside sigma E. Find an expression for the potential. So, we're trying to basically solve this, but if you look at the voltage, intracellular voltage, as a function of x, it goes up to V naught, 0 down here. We're ignoring the resting potential. That's at B. That's at 2B. 0 everywhere else. Now, in this case, and the other thing that you have is that it doesn't tell you exactly what the current is, but we know it does say that. I'm going to find it in terms of the current, so I don't have to mess with a lot of the other parameters. I guess here's the current. The current is going to be sigma I, this is the magnitude, times the voltage gradient. And the voltage gradient, at least here, if I got to calculate this current, is going to be VI over B. That's the slope. Now, this is the current density, actually. Sigma I times dV dx. And to get the total current, you have to multiply by the cross-sectional area, pi a squared. So there we have the current here. It's going down, so really you'd think, well, why is it negative? But in the relationship between the current and the electric field, there's a minus dV dx. So you end up getting a positive current. The current's going down the axon here. Here's your axon. You have a current I0 going down here. Here, the slope is twice as small. So the current's going to be only half the size. It's spread out over twice the distance. But the current itself is I0 over 2. Out here, current's 0. And out here, the current's 0. Because there's no slope. There's no voltage gradient. So we know what the current distribution. This again looks like a problem you did in your past class. We know how the current is going along the axon. Okay, now I have a question for you. If the current is 0 here and it's I0 here, how much current is coming out of the axon at this spot? Just use Kirchhoff's rule. Coming up with too complicated an answer, you're probably doing it wrong. All the current has to go out. There's no current over here. Current's conserved. All the current comes out. So, in other words, this is essentially a delta function of current, and the total current coming out is I0. Well, there's also some current coming out here. It was I0 over 2, because it was only half the size of the current. Where's the current going in? Right here. How much current's going in to the axon at that spot? Right, 3/2. I0 going in. So we know exactly where the current's going in and out and how much is going in and out. So, and we don't have to really integrate because there's no current going out through the membrane anywhere except at 3 discrete points. So our integral now gets reduced to a sum over 3 points. So VE, extracellular potential, is 1 over 4 pi sigma E times, well, the current itself is this big quantity, sigma I VI pi A squared over B. And now we have to ask ourselves, where are we going to calculate this current? Let's call this point out here x0, y0. That's the point where we're calculating the potential. this is x equals to 0 from the problem is right here. So this is x equals b, this is x equals minus 2b. All right, so we have a current coming out of the axon here. So that's I0, which we've already put in. This quantity right here is I0. So 1 over, and now there's going to be an R. So let's say we're calculating it at, so it would probably be easier if I put this in. Here's your x0, y0. So we need to find this distance. Okay, so that distance, well, y is the direction perpendicular to the axon. X is going to be, what we really need is we need to know this distance. To make this little triangle, we need to know, we're trying to calculate r. And x here is x equals to b, and x here is x equal to x naught. So how wide is this? That's x naught minus x equal to b. This is x equal to b. This is x equal to 0. This is x equal to x naught minus x equals to b. So this length here is x naught minus b. So if this length is y naught, this length is x naught minus b, and you want r, because you have a 1 over r in the equation, you really want x naught minus b squared plus y naught squared square root. That's your 1 over r. Okay, now we need to know how much this current contributes. So we got another r to calculate. So this one's current's going into the cell, so you get a minus. And you got this 3/2. We've already did the I0 and factored that out. What we need now is this distance. Well, that makes a big triangle like this. X is 0 here, x is x naught here. That's just x naught, and that's y naught. You just get x naught squared plus y naught squared. One more. We have a 1 over r all the way out to here. Okay, this is at x equal to minus 2b, really, if you're taking out the sign. This is at x equals x0. So how long is this side?
2xb plus x naught.
Okay, so it's going to be 2b plus x naught squared plus y naught squared. Square root is going to be this distance, because it's a big triangle with this side being 2b plus x naught and this side being y naught. And it's positive because it's coming out, but it's only half the strength. So what you get is a big expression like this. But what does this really tell you now? It tells you exactly what the potential is at any position x0, y0. So we've gained a lot of information. We know the entire extracellular potential distribution. So in your problem 7.1, you're essentially going to be doing the same thing, but you're going to have a different potential distribution. Okay, so, yes?
Is it always positive going out, or does it matter as long as, like if you did going out negative, if you did going in positive, or is it always positive going out and negative going in? You know what I mean?
It's going to be positive going out and negative going in, because if you did it, let's see. Here's extracellular potential. And what it looks like is up, down, down, and then up. And if you did it the opposite sign, you just flip over your potential. But you get the wrong polarity for your signal. So if all you're worried about is how big it is and sort of its spatial distribution, you're fine. But if you're actually worried about the polarity of the signal, you have to have it positive when it come out, because it looks like a positive point charge with electric field lines coming out of it. Well, this is a positive current source with current lines coming out of it. So to get the polarity right, you have to have the positive. Okay, questions on that? Because that is just a way to calculate in a simple example. See, one reason why we do this example is if I told you that the intracellular potential was changing a little more realistically, something like this, then you'd have to actually integrate this function, and that's going to be a little beyond what we're going to be doing. So this is sort of a poor man's way to do the integral by reducing it to 3 delta functions. And then you can actually solve the problem. Okay. Well, this is for a nerve axon, and this looks like a nerve axon action potential. What I want to do now is I want to begin to transfer over and start looking at cardiac tissue. So, last chance to ask a question about this before I erase all this. Okay. Let us move to the heart. Okay, now you have to think about the action potential in any given cell of the heart as a function of time. Well, the resting potential is not too different. And then the heart works a lot like a nerve as far as the way the action potential works. It begins, the M gate or the sodium channel begins to open, sodium rushes in, and that causes the sodium channel to open even more, and you get that rapid upstroke for the transmembrane potential until you get up to about the Nernst potential for sodium. But now here's where things differ between the nerve and the muscle. In that this, well, the way they're similar is this is about 1 millisecond. I've actually exaggerated. This should be, on this time scale, very abrupt. But then the action potential kind of sits up near the top. Instead of coming right back down, it has this long plateau phase until it finally comes back down to rest. And this whole duration, it's like 300 milliseconds. So the nerve action potentials generally get done in a millisecond or two. The cardiac action potentials sit up here for a long time in the plateau phase. Now, a little more about cardiac action potentials. If you calculate their speed, they don't propagate very fast. About half of a millimeter per millisecond, or in other words, meter per second. Half of a meter per second. So that's kind of like this, that speed. They don't propagate too fast through the heart. And their rise time is, like I said, about a millisecond. But these are in humans at 37 degrees. It's actually more like half a millisecond, just because the temperature is higher than, say, the squid nerve axon. So the rise time is pretty fast. But the fall is hundreds of milliseconds. This means, let's think about this. The heart wall is maybe 10 millimeters thick. 10 millimeters thick, half a millimeter per millisecond, takes about 20 milliseconds to go across the heart wall. 20 milliseconds is a lot shorter than the duration of the action potential. So to a good approximation, you only have the upstroke and you never have this repolarization happening at the same time. First, the whole heart's polarized, and then later the whole heart's depolarized. So what we're going to approximate the transmembrane potential as is like this. We're going to only worry about what happens during the upstroke, and we're going to assume it then is constant. Constant before, maybe minus 65. Constant afterwards, maybe plus 40, something like that. And this is a function of time, and this is about 1 millisecond. And we want to see what extracellular potential looks like for this action potential. So, remember with the nerve, we saw there was there was currents coming out during the upstroke, but then there was also something coming out during the return. We're going to ignore all the repolarization phase. Okay, another thing we're going to do in this case is we want to look at large distances from the heart, because you're usually going to be measuring your electrocardiogram out on the surface of the body, so you're, to a reasonable approximation, you're quite a ways away from the heart. You're not real close. So we want to look at what's known as the dipole approximation, where we assume we're a long ways away from the heart. And we're going to see how that approximation comes in. So let's begin. We'll start with just where we left off before. Sigma I over sigma E, A squared over 4, D squared BI, dx squared, 1 over R, dx. So we're back to this integral. And we're actually going to have to deal with the integral. So right now, for the next few minutes, there's going to be a lot of math deriving this dipole approximation. If you don't follow all of this math, well, make sure you know the final result. But I want to show you now how you can approximate this and evaluate this to get the extracellular potential from the heart a long ways from the heart. So let us try this. Let's draw the picture. We're going to look at only one small region along the heart, like a fiber, but the heart's actually a big 3D object. This is x0 here. Here's where you're measuring. This is going to be a distance little r, and this is going to be at some angle theta. And we're going to have to integrate over the heart, over the region where, really over x, the region where the upstroke is. And that region is going to be occurring, say here's a small region, it's also going to be occurring over a region along here, but we're going to assume that this region where the upstroke is occurs over small distances compared to r. So at some specific distance where we're at right now, so this is at x, we have to find what this r is. That's the r that's in here. We want to find the distance to this region and then integrate those over this whole range. All right. So what I need to do is I need to look at this little triangle here. Here's R. Here's big R. Here's theta. And this distance is x from x equals 0 out to x where we're integrating along. Okay, and what I really need to know is I need to know big R, because that's what goes in this equation. So here's something that you can pull out of your old trigonometry from high school. There's something called the law of cosines. It's very similar to Pythagorean's theorem, but this isn't the right triangle. So what it says, if you want to know this side, the length of that side squared is the length of this side squared plus the length of this side squared. And that would be the end of it if it was Pythagorean's, but it's not a 90-degree angle, so you get minus 2rx. So r is, you find r itself, it's a square root of r squared plus x squared minus 2rx. And then there's the cosine theta comes in. It's the law of cosines. So you have this just trigonometry, just a result from mathematics, or a triangle. Okay, I want to assume that r is really big. So I'm going to factor, and that's a little r, out. I'm just going to factor it out. We'll see why here in a minute. If you factor a factor of r out, well, that means it was r squared, so this first term becomes 1. This didn't have any r squared in it. So this term becomes x squared over little r squared. This term only had 1 r. So if you factor it out to get an r outside, you really need to factor an r squared. So you got to get a r downstairs. All right. So we're making some progress. Now, we're assuming you're a long ways away. What does that really mean? That means when you're integrating, this r is going to be much greater than x. as you integrate, because there's some place you're going to stop integrating. This is going to be flat, and you have no source. So the region that you're integrating over is going to, we're going to assume that's small compared to little r. So x over r is always going to be small. Well, that means x squared over r squared is really small. So we can ignore the x squared over r squared. This is going to be small, but it turns out that we can't completely ignore this term for reasons we'll see in a minute. So I'm going to keep this term, but I'm going to ignore this little term because it's doubly small. Okay. Now, what do we need? What we really need is 1 over r. I don't think the reciprocal of that, okay. We're almost there. This is a complicated thing to deal with, this square root, this business. So let's use a Taylor series. This is a place where you have to use a Taylor series. 1 over 1 plus z square root. If you work the Taylor series of that out, it becomes 1 minus z over 2, or z a lot less than 1. If you don't believe me, take your calculator, put in a small value for z, say 1/100th. If you take 1 plus 1/100th, you get 1.01 square root reciprocal. You get 995037. And if you take 1 minus 0.01 over 2, 1 minus 0.01 divided by 2, you get 0.995000. They're really close. And it gets even closer as z gets smaller. So you got the correct Taylor series here. So what are we doing? We're going to go 1 over r. And now this comes upstairs and becomes 1. Here we had a minus, so z was minus, so now z becomes plus. Here you had a factor of 2, who's going to cancel that factor of 2. X over r cosine theta. And now we have an expression for 1 over r. All right, so we're getting there. So, VE is equal to sigma I over sigma e. I'm copying this down. A squared over 4. Integral d squared vi dx squared. And now I got this thing for 1 over r. So I'm going to get an r, which I can pull outside. But I can't take out this x because I'm integrating over x dx. All right, so I'm going to have to erase and get some more space. But at this point, people following the derivation so far. Okay, so let us now, I can get rid of this because I just copied that down. I can get rid of all this because I've already used that. And this is all part of the derivation. You don't need that stuff. Okay, so I will write this now. dE equals sigma I over sigma e a squared over 4r. And now what I'm going to do is I'm going to look at this term. I got 2 terms here. So let's divide it into 2 integrals. The first term is just the second derivative times 1. So I can kind of get rid of partial derivatives because it's really only talking about space. And times 1, so that's dx. And then my second term is going to be this one. But x, cosine theta and r don't depend on x, so I can take them outside the integral. And I'm left with d squared vi dx squared times x dx. Okay. Believe me, we're getting close. But what we need to do now is we need to integrate these. Okay. Does anybody know what the integral of the second derivative is going to be? It's going to be just the first derivative. Integration and differentiation cancel each other. So you get the first derivative and the first derivative at the endpoints of your integration scheme. And out here at the endpoints, a long ways away in this direction, the first derivative is flat because that doesn't depend on x. And out here it's flat. So this term, which goes as the first derivative at the endpoints, is going to go to 0. This term we have to worry about. So now we don't have just a first derivative, we have a first derivative on x. So what we need to do here is, anybody want to make a guess on what your next move is to analyze this? If you can get this, you're really on the ball. Pardon? It's not quite the product rule because we're integrating and not differentiating, but it's something sort of analogous to the product rule for integration. Backwards product rule is not a bad description of this.
Integration by parts.
Integration by parts is what amounts to a product rule for integration. So remember, your integration by parts, you're going to define some things as u and some things as v. Now this is where the math gets a little tricky if you don't remember integration by parts. Now I'm going to call this x u. And I'm going to call second derivative times dx is dv. And then when you're doing integration by parts, what you want to do is you find du, which is just dx. And then you want to find v, which is just the integral of this. Well, again, the integral of the second derivative is the first derivative. And then you have to use the integration by parts. This is basically, this integral is u dv. So integral of u dv is equal to u times v evaluated at the endpoints minus the integral of v du. That's the whole integration of the part by parts trick. So ve sigma I over sigma e a squared over 4r. This went to 0. Here we have a cosine theta over r. And now we have to do this integration. We start with u times v, which is x times d squared vi dx squared, evaluated at the endpoints, minus integral of v, which is dvi dx, times du, which is just dx. Okay. This again, this has an x in it, so you might think, oh, an x goes to infinity, you're in big trouble. But this is the second derivative, and this out here we're assuming is flat as a pancake, so it has no second derivative. And actually that's going to go to 0, we'll assume faster than x gets big, which means that this term goes to 0. And what we have then is we have this integral, which is just the integral of the derivative, which means it's just v evaluated at the endpoints. It's got a minus sign, but if we take the difference between the endpoints and we take vi minus dz, depending on how we define the delta v, whether from top to bottom or bottom to top, we can get rid of the minus sign. And what you just get is the change in voltage from one end to the other. And there is, because we're assuming this is rest and this is the peak. So your final result is going to be sigma I over sigma e a squared over 4r, and there's a squared cosine theta, and you're going to get basically a delta v. Delta v is this change in the action potential, about 100 millivolts. Okay. Not quite at the end, but if you've been sort of stuck on some of this math with integration by parts and all this Taylor series, the hard math is over now. So even if you got lost, take this as just a given, and let me show you what we can do with it. We can now take, multiply top and bottom by pi. This gives you now sigma I, a squared pi delta v. We'll put that all in parentheses. And I multiply top by pi, so I multiply the bottom by pi, 4 pi sigma e. And then you get cosine theta over r squared. Oftentimes people will take what's inside these parentheses and just define it as a dipole moment. Dipole moment is defined as this. It's really, the units are basically going to be current amps per meter, I believe. Let's not worry about the units right now. This becomes P over 4 pi sigma e cosine theta over r squared. So P is some strength, source strength. It really depends on the size of the action potential and how big the heart is and the conductivity. The dipole follows us r squared. A point source follows us r, but a dipole, which you can think of the dipole as being current is coming out here, going in here over a very small distance. A long ways away, this looks like, doesn't look like a single charge. There's no net current coming out. The same amount that comes out within, but they're separated by a distance, so this is your dipole source. It amounts to a dipole P going down the axon like that. Cosine theta just says the potential is going to be big out here, but if you come straight up along this axis, theta is 90, 0. That's going to be because the positive and negative sources are exactly the same distance away. You get 0. And then you get a minus sign back over here. So the way the potential will look will be something like, you have your cosine, so it's going to come up like this. It's going to fall off as you get a long ways away because r is falling off as you move to x longer and longer. But the cosine theta is going to make it positive over here and negative over there, which kind of looks like the second derivative of this thing, as it's supposed to. So you get this dipole behavior, and you can actually write this in a slightly more general way. If you give the direction of this dipole as being along the axon, you can write it like this. This is how you usually see it written in books. P dot r, dot product, over 4 pi sigma e r cubed. Now why r cubed? Because you have a factor of r up here. This cancels one of the factors of r cubed down here. So it still falls as 1 over r squared. P dot r is just the dot product, gives you the cosine theta. So you'll usually see in a textbook this written as the extracellular potential from a dipole source. The important factors are it falls off as 1 over r cubed, so it falls off rather quickly, and it has this shape of sort of a second derivative, positive on one side, negative on the other. And that is the extracellular potential from the heart. It looks like a dipole. So what you'll often be assuming is that even though the heart's kind of a big complicated thing, you'll often just assume it has a dipole associated with it, and that dipole produces a potential that looks like this. So a lot of work to get the dipole result, but now we're going to be using this over the next few days to try to understand the extracellular potentials of the heart and the brain, especially the heart and the electrocardiogram. Okay. This class is probably one of the most mathematical of the whole semester, with all this integration by parts business. And if you get through this class, you can probably handle anything in the whole semester. Now, questions on this? Questions on the derivation? Okay. Last thing I want to do is I want to look at 2 of the homework problems, and then just give you some hints on those, and then we will be done for today. Okay, let's begin with 7.1, which is in your first problem in your homework. And 7.1 is a lot like 7.2 that we worked in class. The only difference is that it looks more like a dipole than a nerve action potential. So we have, here's x equals to 0. You have a current that goes down I0 between x equals to b and x equals to minus b. It's uniform current. Everywhere outside it's 0. And this looks like that upstroke of the action potential that we saw. So over this region, it's more like an action potential that rises linearly. Sorry, kind of like this. So in this region where it rises, you have a current going down. Outside that region, it's flat and you have nothing. So you're going to do it just like we did in that first problem in class. All this current has to come out here, and all that current has to go in there. So you have a source at x equals to b and a sink at x equals to minus b. Now, if you let b shrink down to 0, you get dipole result. But what you want to do in problem 7.1 is to do it not assuming a dipole, but assuming that all the current is localized to this point and this point. So you essentially have 2 values of r to calculate, and this one's positive, this one's negative. Just do it like we did problem 7.2 in class, but for 2 sources and sinks. And you want to get the extracellular potential. So you're going to end up finding v of x, y. Okay, so the way that works is very similar to what we did right at the start of class. Then it goes on a little further. It asks you to find the current density outside. Well, if you know VE, then you can find the electric field outside. It's just minus dVE dx. So you found VE as a function of x, so you can differentiate it. It's a little bit complicated because, as you recall from that other problem we solved in class, it had a bunch of square roots of x squareds plus y squareds, things that. So you have to do a little differentiation. You can find VE, and then you can find JE, which is minus sigma. That's just multiplying by a constant, the extracellular conductivity. And you can find the current density. And then it wants you to find the current density at x equals to 0. So at this point, you set in x equals to 0, and you look what you get for your current density. And that's homework problem 7.1. So again, if you're not quite sure how to get started, go back and look at what we did for problem 7.2 at the beginning of class. Look in your notes or on the video. You'll see it. The other one I wanted to mention was 7.10, the second problem in your homework assignment. This one is kind of interesting because you're going to assume, here you have tissue, like the body, here you have air, and you're going to be assuming you're going to be measuring the potential along this surface. And down inside the tissue somewhere you have a dipole, P. So what you can do is you can find what the dipole is. It's going to be, we're going to assume it's at this depth, which is known. Actually, no, we're going to assume it's at a depth d, but we don't know it. In fact, the whole goal of the problem is to figure out how deep this dipole is. you think of this as a heart. It's a little nicer to think of it as the brain because you're trying to find where in the brain your neurons are active. So you're trying to find the depth of the active neurons in the heart, in the brain. So what you're going to do is you're going to use the equation that we found, which was P dot R 4 pi sigma E times R cubed. Let me get you started on this. We're going to make a coordinate system here. So this is going to be, what did I use? I used this for Y, and this is X. And you're going to say that the dipole is pointed entirely in the X direction. So you can think of this as the magnitude of the dipole times I hat, the unit vector in the X direction. And you're going to say R. I need to know what R is. And R is going to be, you're measuring on this surface, so it's some R like this, which is going to be X times I hat plus D times J hat. You move over X and up D to get R. So, P dot R. P dot R is just P times X. This doesn't contribute because P is always in the X direction. 4 pi sigma E. This is R cubed. That's the magnitude of R, which is X squared plus D squared R cubed, 3/2. Basically, R is square root, and then you cube it. So what you have is an expression for VE along the surface. If you plot that, so what's it look like? Well, when X is 0, it's 0. And when X gets huge, this X squared to the 3/2, this falls as X cubed. It's going to dominate over that. It's going to go falling as X squared. So you look something like this, and negative on that side. So the dipole signal looks like this. That's what, if you measured over this surface, you'd find. Now, what you're trying to do is you're trying to figure out how deep the dipole is. So what you're going to do, and what the problem sort of outlines for you to do, is you're going to figure out where this is at peak. You have an expression for VE. So find the peak of it. You take the derivative, set it equal to 0. You can figure out what the value of X is. And so you can figure out what 2 times that is, which is delta X. And you can relate delta X to D. And your whole goal is to find a relationship between delta X and D. That's what the problem really asks you to do. Find an expression for the depth D of the dipole in terms of the distance delta X. So what's the idea? The idea is, think of this as the surface of the scalp, and you're measuring the voltage over the surface of the scalp with electroencephalogram electrodes, and you measure that voltage, and you find it has this shape, and you measure the distance from the peak negative and the peak positive. And that way, you can then, if you can solve this problem, you can relate that distance to D, the depth, and you can tell how deep your dipole was. So you can say, okay, this person has an electrical problem in their brain, and that electrical problem is 6 centimeters deep. Oh, I know exactly where in the brain where it is. So it can be a very useful thing. So that's a little outline of how to get started on 7.10. Your ultimate goal is to say that delta X is equal to some number times D. It's a dimensionless number which you're supposed to figure out that can relate D and delta X. Those are the first 2 problems. The rest of the problems will have to wait a while before we discuss them. But what we're going to do in next class is we're going to begin to talk much more qualitatively about how you can use these electrical information from specifically the heart in order to learn how the heart functions. And eventually, we're going to be trying to diagnose electrocardiogram problems. All right, so that is it for today. I will see you on Wednesday, and we will move on talking more about the